This is basically using our program Electro. You can solve two-dimensional models and rotationally symmetric geometries. It is a very easy to use program. I will show you. I will start with a very small problem. Uh, Afterwards, I can show you with uh, uh, big models. I will show it here. So now, in our program, you can create the geometry, any model you can create here, or if you are interested only in importing the geometries from your CAD programs, you can do that. You can come to files and CAD imports are available here. SolidWorks, Pro Engineer, Inventor, Solid Edge. Suppose these five direct links, but suppose if you don't have this CAD programs, you are having a different CAD program, what you can do is you can save the file in your CAD program in IES or DXF or STEP format, and you can open the files in our program. Anyway, first I will take a very simple model. First thing is you can choose any units you like, and you can change the units at any time you like. So I am considering centimeters here. Next, I will take a, a circle command. I create a circle here, then and another circle here. Then we'll take a rectangle. Okay, I am not spending more. I'm not elaborating what I am doing in the geometry part because there are all are very self-explanatory. So those things I'm not spending time. Next, because the electric fields they will be singular when you have a sharp corners. So what I do is I want to round these corners. Go to modify round corners. Okay, this point, this point, this point. So I want to round with a 5 centimeters radius. I want to round it. Done. Then I assume this is my geometry. The top circle is a high voltage and the bottom circle is 0 voltage. And this rectangular block I consider with a dielectric material. So I go to physics material table. Let's say here we got some built-in table. If you want, you can add any number of materials. I want to put this is aluminum. These two are aluminum blocks. Then next, I will take this is a porcelain. This is porcelain. Let me see what are the properties of porcelain we have here. Permittivity is there are 6. Right now I am using in a permittivity mode. I only care for the relative permittivity 6. Or if you want, you can change it like that. We can input whatever permittivity you like. Then afterwards, then go to physics. The next thing is boundary conditions. The boundary conditions, I say this region is 10,000 volts. Okay, this one is 0 volts. That's all. My problem is a very simple problem. 10,000 volts on the top, 0 volts on the bottom, and see. Next, come to solution setup. If you see here, we got in our program we got 2 options. One is boundary element method, another is finite element method. Boundary element method is we solve the Maxwell's equations in integral form. So you need to put mesh only on the boundaries. The surfaces having boundary conditions and material interface. For example, if you consider here physics material, here you see See this block is a porcelain block. So this segment or the periphery of this porcelain block, it is separating two materials. Outside is a vacuum, inside is this is a porcelain. So here this boundary, this periphery of this is this material interface condition. So it will put elements only on that. So and you don't have to put the mesh in the entire space. You don't have to put the spacing of the mesh in the all this region. It happens only for the finite element methods. See here, if I choose finite element method, it will put the mesh in the entire space. That will be a 2D mesh. But whereas I'm preferring boundary element method because that is best for electrical engineering problems. Okay, then everything is self-adapt. So you don't have to put the mesh. It will automatically put physics run solver. Now see here, it is already put the mesh here. These are all 1D elements. The mesh is only the small segments, pieces of this. That what you are seeing. There is no mesh outside. That is the speciality of the bound.
Yeah.
Okay, please hold a minute. Okay, let me see this. Okay, some people, okay, let me see here.
You will have to you want to mute.
Okay,
You just do mute. If you
mute out, finish. Everyone. Okay, everything is muted. Okay, sir. So once the problem is solved, then we will calculate different types of displays you can make. Let me do first the simple and very interesting 2D contour plots, plane contour on. First, I will take it very fine. Let me plot this. So here, color contour plots, solid color, apply. Can you see this? Put scale. If you see this, see now I have 16 contours with different levels. The first contour, the brick red color, is varying from 10,000 volts to 9,330 volts. That is the range. So then other colors accordingly, the ranges will be shown here. If you want, you can increase the number of contours like 30. If I make it 30, now can you see here, now the more bands will be there. Accordingly, each band, it will become narrower. Now, if you see here, okay, let me go back to color contours, color lines, apply. See here, suppose if you are not happy with the smoothness of this, we can choose another option here. Option, delete all plots. Now what I do is this time I will take user defined grid. Okay, new plot. I say along x direction. Let me put this way. 1 minute. In the along x direction, I will put 200 points, sampling points. Along the y direction, 100 points. Now I am using this. You see, now can you see that the lines are more smooth? Now anyway, so you can see the contour plot like this, and see the accuracy. Like you see here, if you observe, I don't know how many people can watch this. I applied 10,000 volts here. After solving the problem, you got 10,000.56 volts. So that is 0.56 out of 10,000. That comes to something approximately, okay, take away 0.0056% accuracy. 0.0056% accuracy. So that is the beauty of the boundary element method. Finite element method gives good results, but the accuracy when you compare boundary element method is more accurate than compared to the finite element method. Anyway, now okay, let me delete all these plots. Next, I want to show the electric fields. I want to see the electric field, that is most important. Now here, I will take arrow plots. Okay, let's take a very fine. Can you see? Okay, I will change the aspect ratio a bit. Or make it a line. Can you see here? So the electric field at any point, you can see that its direction and its value. For example, here, value at a point, if you put your mouse and press a left button here, you can see its x coordinate, y coordinate, x component of the electric field, y component of the electric field, and its resultant. So electric fields you can calculate in form of arrow plots, or let's go here. Let me see here. Option, delete all plots. There is another small interesting plot, is a scatter plot. Sometimes it will be useful. Let's say medium plot. Okay, see each ball, that is sampling point. Let me simply reduce the magnitude here, the ball's magnitude. So now the dots indicates the range of electric field what you can find here. So scatter plot. The most important thing for any engineer is the graphs are the most important. For example, graph along a line. Let's do this. See, in this problem, if I want, what is my electric field starting from here to here along that line? So this is the electric field along this direction, x-axis. This y direction, in the y-axis, electric field will be there. Now, if you put your mouse, can you see on the left side the location of the physical location of the graph it shows? See, as I move my mouse, you will see a blue dot on the picture area. So that is the location. It's at this place. The electric field is 0.3 10 to the power of 4 volts per meter. I want to say one more thing here. See, I want to change here. Let me go here. Utilities. 1 minute. Okay, I'm here. Okay, utilities, units. I want to change the units here. Electrical units. Electric field, I want to see in kilovolts per centimeter. That is my preference. Okay, that's enough. So automatically the units will be changed. Now if I press here, now my electric voltage at this point, observe there is a blue dot on the picture on the model area. It is 3.4 10 to the 0.034 kilovolts per centimeter. So you can draw graph at any place. And another point I mentioned here, because we are using the boundary element method, you can calculate the graph or the results anywhere. There is no limit because there is no artificial truncation of the region. But whereas in the finite element methods, when you are using, what will happen is the problem will be artificially they truncate approximately 5 times bigger than the model area. They put an artificial region. You can see the results only within that region, but not outside. But whereas in the boundary element method, you don't have that problem. Now, another thing. So, for example, here, let's say, for example, freeform curve. I want 1 minute. The geometry, freeform. Imagine I want a curve like this. Okay, this is a freeform curve. If you want to calculate the results along that freeform curve, you can do that. So now select, okay, select, 1 minute, new graph. Let me see. Okay, now, okay. Can you see here now? I want to go start from here, go down all the way at every point here. So now, so this is the electric field at any point you like. So you can put any curve you like, or you can calculate the graphs. Then another display form people mostly interested is uh, to see how the electric fields are uh, grouping that we call as streamlines. For example, let's say we'll put 100 streamlines. Here, draw maximum length. Let's put suppose some 400 centimeter maximum length and make it very fine. Okay. Now, okay. So on this, can you see here? Underlay medium. Can you see here? So these are the, can you see the electric flux line when it comes, when it hits the dielectric material, it will take a bend. Depends upon its dielectric constant. So the streamlines, it will be very useful. They will be useful for you to understand where the flux is getting concentrated. So this is a basic. Another here you see here physics. The problem I solved is a 2D problem. I think I made a mistake. I should have told you right in the beginning. I am solving a 2D problem. This model is assumed to be infinitely long. We are taking a cross section, and because the fields are invariant along the depth of the model, so we are taking a cross section and solving the problem. That is the result what I showed. Now what I do is the other problem, other type of problem that we can solve in electro is rotationally symmetric. I will take y-axis rotation symmetric. Okay, I say okay. So what I do is modify, delete everything. I'm deleting this. Okay. Now I will create a rotationally symmetric geometry. So in the rotationally symmetric geometry, what we do is we will enter only one radial section. One radial section, we take it, we'll enter that, and we now in this problem I'm taking y-axis is the axis of rotation, this axis of rotation symmetry. I will solve that problem. The units I like to choose in this case is inches. Okay, I will take because this insulator problem is very commonly this program is used to simulate insulators very commonly. That's why for this rotational symmetric problem I am solving a insulator problem. Okay, first I will a very basic problem entering. Okay, 0.75. Okay, one rectangle here. Then modify. As usual, I want to round the corners first. This is the corner, 0.25. Okay. Then next, break by length. I am breaking this. You will understand why I am breaking this. 4.75. Once I complete the model, you will understand. That is the break point. Similarly here, Okay, that is the breakpoint. Next, I want to create the sheds here. Sheds I am taking as a semicircular sheds. Okay, okay, x, y plus 1. I drew a line there. Then geometry, circle, tangent to this. That is the point, uh, 0.825. So I will take that circle. Then, okay, modify, break by number. Take that, break it into 4 pieces. Then delete. I don't need this segment anymore. Take it out. Copy on. Copy off. I think I want copy off. Okay. I will take this one, this one, this one. Put start from here to here. Okay. Then this one I take it from here to here. Okay. So now I got a part of shed. I got. Please see here. The shed I am taking as a semicircular. Just because I want to take a very simple problem. That's why I'm doing like this. The next thing is copy on. Okay, mirror. Put a box for selecting the entire thing. Then this is the thing. X plus 1y. That is the mirror line. Copy on it there. It is mirrored. Okay. Then we take copy on this there. Okay. This one. Copy here. Okay. So now, basically, that's all. This is the problem. Now I will add this extra lines here. Okay. So imagine that now see this. This is the axis of rotational symmetry. This is the axis of rotational symmetry where my mouse is moving. This is the axis of rotational symmetry, and this region. Okay, this region is my high voltage. This region is at 0 volts, and this region, this is a floating potential. This is a metallic piece. I don't assign any voltage. The program will find it out, that voltage. Let's see. Physics, material. Okay, this time I want to use mica. This is, no, let's use something very silicon rubber. Usually that is the material they use it. Silicon rubber for sure. 1, 2, and because we are applying boundary condition in these three material, whether you assign materials or if you just leave it like that, it makes no difference. Just only for artistic reason, I'm adding some color to this. Here. Okay, aluminum. Everything I made it is aluminum. As I told you again, because I'm going to assign boundary conditions for these three blue blocks. So when you have a boundary condition for the entire region, there is even if you put any material, that information is not used. Okay, then physics, boundary conditions, voltage. I say this here, I will use 10,000 volts. Okay, here 0. Okay, next floating conductor. This is floating. I will say number 1. Okay, just for you to understand, it is just slightly. I am putting a small. Okay, we'll do like this. We'll put a ring here. Okay. So why I call this a ring? Don't forget that this is the axis of rotational symmetry. Once you take the axis of rotational symmetry, if you have this ring, if you revolve around that axis, what will happen is you are going to get a donut. It is something like a corona ring. Okay, this will become a corona ring. But Usually what they do is corona ring, there will be a connection between the corona ring and the high voltage, but I am not putting that connection. The reason is uh, usually the connection they will put it, once I put that connection, it will lose the rotation symmetry. So that's why I'm not putting. What I can do is I'll go here material. No, not okay. Let's put material just for again artistic purpose, or put a different kind of material like steel. Okay. Anyway, it is of no use there. Then physics, a boundary condition. I will solve this problem in two different ways. I will solve the voltage. So this is I put same 10,000 volts. That means what? Though there is no physical connection here, because here we have put 10,000 to this region, here also 10,000 I applied. That means the both two, though they don't have physical connection, they will be at same potential. Okay, that's good. The next thing is here, okay, I think we have already done. This is rotational symmetric. Okay, please see here, ground voltage sources. That the meaning is in the in the this happens only for rotational symmetric problems, not for the 2D models. 2D models, so I will show you here physics. Suppose if I make it as 2D, automatically this got grayed out. What it means is in a 2D model, the charge is balanced. The meaning of that is whatever the charge, the equivalent charge, we assign only voltage. What we do is in the program, we will calculate what is the equivalent charge that supports the boundary conditions. So what will happen is in 2D problems, what happens is whatever positive charge is here, the equivalent opposite, that is a negative charge, will be on your lower voltage conductor. But this is automatic. But whereas in 3D case, in rotationally symmetric cases, it is not. You got an option. You can say that there is a ground voltage somewhere at some place that which I don't know. Then you can say that there is a ground voltage. Then what happens is this is it. Whatever you are giving this blue color is at 0 volts, and also in addition to that there is a ground at far off place. Okay, that is implied. Now, okay, let's take with that first. Now let's solve this problem solution. Let me see again. Solver setup is boundary element method. Let me solve this solution from solver. Problem is solved. Uh, now the first thing I want to know, because okay, let's do this way. This region, okay, I want to see when I say floating potential. Okay, let me do this contour plots in a region. See, this one we called as a floating potential. At what voltage that region goes? Let's see. Let's see. So in the, it is basically 4.714 to all, say 4.71112. That is 1 in approximately 5,000. That is this entire block is floating at 4,714 volts, or the average value is 4,713 volts. We did not assign. The program calculated this. Okay. Now, see. Okay. Just okay. Remember this. Let me write down this so that you can compare it. Okay. Settings or text. Okay. Text on. Okay. Settings 20 bold black color. Okay. let me do this. So 4713 volts, okay, with ground, with grounded voltage, ground, with ground, okay, with ground. I will put this. So that's enough. It is. So you note down this. Let's record this stuff here. The next what we do is same problem. What I do is this time solution. I remove it. I will disable this switch. Let's solve this problem again. Run solver. Now what I'm saying this time is whatever charge, because now the charge is balanced. The higher voltage electrode. This is a higher voltage electrode. This 10,000. Whatever equivalent charge is there, that will be positive charge. Then this will, on this bottom, it will have exactly equal and opposite charge. In such case, what will be this floating voltage I want to see now? Can you see here now? This is 5,589 or 88. One in approximately 5,000 variation. So it is basically now I got, let me see here, option, okay, not this one. Utilities, text. I'll put, now this voltage is, 5,588. Let's put that. Text. Now there is a lot of difference, like approximately 3 plus 6, 900 voltage is difference. So here I want to stress here is in a problem where there is a big ground is available. For example, in our practical problem, especially these transmitting towers, you will have your transmitting tower which is connected to the ground, and the ground is at zero potential. So that is, so for that kind of cases, we should do, we should turn on this switch, grounded voltage sources. For example, if you are having a case where your model is small and this model is nothing to, and you are operating with a battery, one is a high voltage, another is a reference voltage, nothing to do with the physical ground, then you have to disable that ground. So this is a both this thing has to be done only in the RS problem, rotationally symmetric problems, not in 2D. 2D is always, it is a balanced, charge balanced circuits. Okay, sir. Now I will go back to again here, because in usually rotational symmetric problems, there will be grounded voltage sources. I want to resolve this and solver. Okay, done. Now I want to see what are my electric fields on the insulator. I want to see now, like electric field graph. I want to see in a graph. Okay, graph in a segment. Let's see here. Okay, usually the electric field will be higher, closer to this. Okay, program is asking, and you want to see on both sides of the selected segments or only on one side. I want to select on both sides. I will select. So right button. So this is the direction. Start from here. No, I want to go other way. I start from here and go here. Let's see what happens. Can you see this? The red color indicates usually, see, because the higher field will be on the free space or the air side. The lower field will be on the side of the insulator. Here we have used porcelain. So the black color indicates the thing. Here I'm using magnitude. So the fields here, they are in the order of something like 5.5 kV per centimeter. These are the electric fields on this. Let's see here. I want to see the arrow plots, the electric field. The most important is what are the electric fields on the high voltage electrode. Let's see. I think first we'll take the graphs on this. The electric field will be on side of A. Okay. Can you see that? So somewhere here, obvious, understand that because there's a segment which has got a rounding there. The field is maximum at that place. That field is 10 kV per centimeter. That is the field there. And second peak is coming again on the second rounding. Okay, I will make it larger so that you will see this. See, the first peak is also, why not we do one more thing? Let's make it more number of points so that the curve will be smooth. Okay, let's see here. Okay, on the side of A. So that is the direction I like it. Okay, now, yeah, same thing. 10 kV. No, 1 kV. 1 kV is 1.01 E00. So this is 1.01 kV per centimeter at that place, right at the middle of that corner, and middle of the next, not at the middle, somewhere closer to the lower side, if the second peak is there. So you can calculate the electric fields at any place you like. Okay. Now the corona ring at this place, let me see here, physics. What kind of boundary current? We have used 10,000 volts we have used here. Now just for, okay, I'm applying, this time I'm not using 10,000 volts, I'm applying a boundary condition, floating boundary condition. Okay, now let me solve this problem again. Now this time the corona ring is not in contact with the high voltage. So this program will decide what is the voltage it will go. Solution, run solver. Okay, now with this condition, what will happen to the electric fields here? I want to do same graph on the, okay. 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 Can you see that the new curve is almost double. This 2 this is 2.12 kV per centimeter. The black curve is when this is 10,000 volts and this is also 10,000 volts. Then you have approximately 1 kV per centimeter. When you have, this is just a aluminum ring which is not connected to this, then the fields have jumped almost double, slightly over double. This is understandable because when you have 10 kV here, 10 kV here, what will happen? Then definitely the fields within this region will be smaller than when you don't have a when you don't apply a voltage. Now this corona ring floats at some voltage which is different from 10 kV. That's why it has got high electric field. Okay, I will close this or let it be like this. I want to see values at a point. What is the value of this here? The electric, okay, it shows electric field. Okay, make it voltage. I want to see scatter pattern. What is the, okay, in this region, the corona ring, how much? Yeah, this is, okay, move. Yeah, practically, okay, let's make it, Okay, can you see here? This is 5.59 10 to the power of 3, approximately 5,590 volts. It floats at 5,590 volts. Okay, so this is basically a 2D problem I showed to you, and a 2D cross section. And this problem, the problem you're seeing on the screen is a rotational symmetric geometry. Now let's do option delete all plots. Okay, now the curve is already, you take this curve out. Now I want to see contour plots on this problem. Okay, make it very fine. Not regional, plane will take. Okay, very okay. Can you see? So because though you have not modeled because we modeled only on the positive side of the axial side. Do this here. So here, see, we did not model anything to the left of the axis, but the results will be automatically calculated on the left side also. Okay. So this is a rotational symmetric problem. Now I will show you some of the practical problems that you can solve with Electro. First problem I'm showing is this uh, high voltage insulator, a practical problem. Now, okay, I'm not saving this. Okay, so okay, let's save it. Oh, okay, okay. 1 minute. Okay, this is. Let me see. Not this, not this. Let me see. Electro insulator. Let me see. Yeah. So this is a very practical problem. In this, what we have is the axis of rotational symmetry is along the x-axis. This is the axis. Can you see that green line? That is the axis of rotational symmetry. Let's go here. Physics. X-axis symmetry. And in this case, I don't know why they take a grounded voltage. We will change it. We will see what is the difference. Okay, now, so here, physics, materials, let's see. So here, material, inquire. This material is silicon rubber. All the shirts are silicon rubber. And this is nylon 6 fiberglass edit. It has got a permittivity of 4. And this silicon rubber edit, it has got 3.45. And this they put as a copper. This is only beauty purpose because they put a boundary condition there. And this corner ring here, okay, these are all low, zero. Okay, I think this is the high voltage side. This is the ground voltage here. Let me see here. Physics, boundary condition, display. Yeah, this is the corona ring. It is got 1.3 to 10 to the power of 5. This is 132 kV. 132 kV. And this side, this is 0 volts. Now this problem is already solved. Let's see here. Solution, solver setup. Everything is self-adapt. And now you see here self-adapt accuracy, put 001. Our default is 0.01. That means 99% accuracy. When I put 0.001 means it's a 99.9% accuracy. Now solution elements, 1D elements, it has taken, okay, these are the one program put by itself, 5,000. Can you read this number on the lower I'm highlighting it, the lower left corner. 5,455 elements it has put, and it solved the problem. And now let's resolve this problem again. how much time it will take, I want to show it to you. Elements, delete all, delete all. Now I want to solve this problem. Run solver. It is solving. Okay. Let's see. The machine I'm using is, it is, let me see, okay, task manager. See, I'm using, can you read here? Intel or Core TM i7. This is CPU I'm using here, and the RAM I am having is 64 GB RAM, but we don't require because 2D problems. Electro needs 8 GB. It is 8 GB RAM is even 4 GB RAM is too much. So problem is solved. Now let's see how much time it has taken. Problem we started at, let's see, we started the problem at 11:55, 11:55:21, or so 11:55:01. 20 seconds it has solved. It solved the problem in 20 seconds. Now, so I want to see my results, the electric field variation I want to see in a graph, in form of a graph along a line. Let's say I want to put 10,000 points. Okay, I want to start from here, go all the way, or I will do this way. I want to cut across all the sheds. Okay, let's see. Okay, see now you see here, zoom the, see the voltage variation. Every time you see slightly flatness there, that is, it is going through a shed. See here, if I put my cursor here, can you see the first, it is entering into the first shed, it is the first shed, then this fall is the free space, then here again the slight flattening, the smaller shed, then it goes to the next one, it go on, so on and so forth. So you can calculate the electric fields. Now we'll calculate the electric fields. I want to see the electric fields in on the corona ring part. Okay, arrow magnitude on a segment. You don't need 10,000 points. Take 100 points. Let's see here. Along this corona ring. Okay, I think then we will do it because when we have, okay, let's put at least 400 points so that we don't miss any. Okay, let me do it. Okay, this is okay. Then, okay, on the side of the air I want. This is my start point. Okay, on the side of okay, this is my start point. So you are having on the corona ring, the electric field will be, of course, the units I think I'm using here. Okay, let me go back here. Make it utilities, units, electric field here, kV per centimeter. Okay, here it has got 6.6. The peak is somewhere there, that it has got 6.46 kV per centimeter. Okay, basically, I think maybe at this stage, I should invite some questions